day everyone, welcome to the course on biological data analysis and visualization with R. We are in the week 8 of the course, and in the last class we have introduced some of the data classification techniques, and one of them is logistic regression. So, we have very briefly discussed how logistic regression works, and then we have seen the one hands on. In this class we will be talking about something called penalized and stepwise logistic regression. So, first we will do another hands on a noise data set, and then we will apply penalized logistic regression and stepwise logistic regression on that data and see whether we make any improvement or not. So, just to briefly remind you, right, we use binomial logistic regression for binary classification, and we use multinomial logistic regression for multi-class classification, which we have done in the hands on, right, multinomial regression, and we can simply use logistic regression function to call logistic regression when we want to do binary classification. Now, one of the issues, as we have seen in case of linear regression, is overfitting, right. So, what is overfitting is the data fits the training data very well, but is very poor at predicting the outcomes on a test data, right. So, this is a problem for many models, and this is something we will see as a recurring theme as we go into the discussion on decision trees, etc. The issue of overfitting is that there might be too many features or independent variables that are being used by the model. Okay. So, when we are fitting the data on fitting the model on the training data, the model is actually utilizing too many features and independent variables, and it is trying to fit the training data perfectly. Okay. So, this is where the problem is. The solution, of course, is then try not to fit the training data too well, right, keep it a bit simpler, right, and more general, which can then be applied on test data as well as variety of independent data sets. Okay. And to do that, we use something called penalized logistic regression. This is something that is we have seen in case of lasso regression or ridge regression, right. So, we are trying to avoid overfitting. There we are trying to remove the multi-collinearity issue. So, there is a penalty term in this model that reduces overfitting, and this is similar to lasso and ridge regression. The other solution we have is called stepwise logistic regression, and again we have seen this. So, we are familiar with the idea in case of linear regression is we stepwise select some of the features, right, that might give us the best performance. Okay. So, this is something here we also aspire to do, right. We take stepwise select, right, stepwise select the features that might give us the best results. Okay. So, what we will do is in this class we will first hands on is gene expression noise data. So, we will first classify genes into specific noise classes, and we will see the performance of this model, and then followed by that we will be doing we will be seeing if we can improve performance by using penalized logistic regression using the package GLMNet, and then we will use the stepwise logistic regression using the R package NNet. Okay. So, this is what we are going to do today, and let us move on to the hands on, and we will start with the R console here. And again we have seen this data before, but very briefly I remind you. But before that, we will first load the libraries that we require. We need the reader library and the tidy models. The data is called filtered merge data east, okay, and we have seen this before, this data, and we have also done some pre-filtering like this before. As you know, we want to remove those columns, right, where most of the values are NA values, right, where we have missing data. A lot of these data points are missing. So, we do not want to use those columns or the data or the features in our model, because those are not going to be very useful. All right. So, let us look into the column names, right. Okay. And one of the things you probably notice, right, we are familiar with these column names, right, gene, average expression, we have noise. What you will notice here, there is a DMYPD class. This is the noise class, right. So, the genes are classified according to this DMYPD class. We can have a look at this, right, what these values are. Okay. As you can see, this is 1, 3 and so on. So, this is actually just 1, 2, 3, right. There will be 3 classes. We can check, right, how many classes are there. Okay. First, let us also filter this. So, which means instead of taking these variables DMYPD or DMSD, what you want is this DMYPD class value, right. And we can look into this as factor. Okay. So, you can see this, right, these are the values we have, and at the end you can see labels 1, 2, 3, right. So, there are 3 classes here. Again, we will apply multinomial regression for sure, right. And so, the data that we need is column 5 here, just to remind you. Okay. So, we need this 1, 2, 3, 4, 5, right, this column 5 we need, and then we need the rest of the features which start from column 7. Okay. So, that is why the next filtering is, right, we are just taking only a part of this data, right, and we need this class information because these are the actual labels, right. So, as we have seen in case of cancer data. Then we are doing a second filtering, right, where we are kind of looking at the features, and features for which the variance is 0, we kind of discard those features because they are not going to be useful for any prediction. Okay. All right. So, we have arrived at this finally, the tab field 2. Okay. And as you can see, we have 2160 genes. These are the number of rows. We have 260 features, and one column is simply the DMYPD class. This is actually the ground truth, right. Okay. So, then we are taking only a part of these features, right, just as like to make it a simpler model, right, but of course, we can run this with all the features that we have in our data, and this is something you can again try out. What we need to run this model is we have to convert these DMYPD class values as factor, right. So, that is what we are doing, we are rewriting this, right, input data $DMYPD class, right, this column we are storing as factors, right. This is what will be required when we apply logistic regression. Okay. So, otherwise you will get an error that will tell you, right, it should be factors and all so on. So, we are doing this beforehand. So, now we have the data. Okay. So, we can simply look at this data now. Okay. The first column is our class, right, this is the label, okay, or the class that we want to predict from the rest of the features that we have. Okay. The next step of course is simply split the data, right, into training data and test data, and we have seen this for cancer data how this works. Okay. And so, we can see this again, right. So, we have 1700 genes that will be used for training data, 434 genes will be used as test data, and the total is 2160, and again the strata should be DMYPD class because every class should be represented equally, right, that is what we want there. And then train, right, okay, train is split training and test is split testing. Okay. So, this is what we have seen before, and we have the training data. We can see simply that dimension train. We can also see the classes, right. So, labels 1, 2, 3 are represented in the data, and they should also be in the test data, right. So, all classes should be represented according to their proportions in the original data. Okay. So, 80% data for each class will be there. Now, let us now run this logistic regression or multinomial regression, and we will be running again on the training data. So, we are running again multinomial regression. So, this will be multinomial regression function because we have 3 classes. If you are learning logistic regression, you will simply need to write logistic regression. It will tell you, okay, mode classification, engine GLM and so on, penalty null, mixture null, etc. Okay. So, we are running multinomial regression. So, again we have mixture, penalty, set engine, GLM net, set mode classification, and this is the formula. The last line is the formula, right. So, where we are giving this DMYPD class, this is what we want to predict, right? The class the gene belongs to, which class the gene belongs to, whether it's class 1 or class 2 or class 3, and then use all the features for doing this prediction here. So, this dot means use all the features. The data that we are going to use is the training data. Okay. And we can look into the data now, type the model, and as before we have these intercepts. Okay. So, intercepts and the coefficients. Okay. So, for class 1 this will be the intercept and the coefficients, class 2 there will be different intercept and coefficients and so on. Okay. And let us see, right, again running through the same set of codes, we can now look into the accuracy, confusion matrix and so on. Okay. So, we are predicting now, predicting class using this model on the test data. As before on the cancer data set we have done this. Okay. And some of the things are giving NA values, which means they are not able to predict those classes. Okay. Why? Because there might be missing data. So, that is something that is causing problems in class prediction. Okay. Now, you might ask, like, what is the solution? If you want to predict something, what will be the solution? One of the solutions that we have talked about is perhaps we can impute the data, right. So, we have seen this before. In case of, for example, where we are using lasso regression, we used imputed data, and so we can do an imputation and then we can try to run this model. So, this is something, again, I will encourage you to try out. Will not be doing this in this class because imputation will take a lot of time. So, this is something that you can try out, but the codes or the commands, the way we are going to do is will be the same, except that we will be loading only the imputed data for our analysis. Okay. So, that might be the reason. So, if you want to, if you work with imputed data, this might look better. Okay. So, again we will be looking at now the predicted probabilities, predicted probabilities or class probabilities. Okay. And we can again look into this. So, sometimes you will see these NA values, right, and again for this sample 5 you see this 0.514, 0.07, 03, 0.415, which means you can see, like, out of these two, 1 or 3, like 1 is slightly higher than 3. So, it will predict as class 1, right. So, this model will predict this sample 5 belongs to class 1, and we can look into this accuracy again, right. So, by okay, so we will first combine these actual labels with the predicted labels or predicted class, right, and here we have. So, for example, here we see this is DMYPD class is 1, it is predicting as class 1, right. For some of them this is NA, of course, we cannot do anything about that unless we work with imputed data. Alright, so we have this. Now, we can look into the accuracy results, right, and the command we have seen is truth is DMYPD class, right, in this results data frame, and estimate is the predicted class, and the accuracy is only 0.375. Okay. So, as you can see here, the accuracy actually has suffered, right. It is not a very accurate model, and this is something that we have to deal with, and maybe we can try to now select specific features or build those penalized models and see whether we can improve performance of this model, right. So, here the accuracy is not very good. The only thing I want to also look at is this confusion matrix, right, whether it is predicting specific class very well and it is not predicting another class that well. Okay. So, as before, the command is confusion matrix, right. So, conf underscore mat results truth equals to the actual label and the estimate, which is the predicted class. And as you can see, this is a very kind of surprising model, right. As you can see, this model is able to predict class 1, okay, 18 samples, okay, they are actually class 1, they are predicted as class 1. There are 12 samples, they are predicted as class 3 and they are actually class 3, but there is a large number of class 3 models that are predicted as class 1, they belong to class 1, okay. That is something that is again a bit surprising, but what is also more surprising is that this class 2, right, is not predicted correctly in even a single case, right. So, here 0 means 0 samples are predicted as class 2, right, and that are actually class 2. Okay. So, as you see, right, some of the samples are predicted as class 2, right, 7 samples, but they are actually class 1, and similarly there are some samples that are predicted as class 2 in this model, but they are actually class 3. Okay. Some of the class 2 models, actually class 2, they are predicted as either class 1 or class 3, right. So, this is very surprising, which means it is predicting class 1 and 3 okay. So, 1 is okay, 3 is also pretty okay, but class 2 is really bad, right. It is very bad at predicting class 2, it is not actually predicting class 2 at all. Okay. All right. So, let us now see if we can improve this performance, and as I said, we will now go into the penalized regression and see whether that will improve this. Okay. So, we will first do penalized regression and then we will do the stepwise regression and see whether we see some improvements, etc. For penalized regression, as I mentioned, we will use this GLMNet package in R, and let us start with this penalized regression. We have the data already, and right. So, here we have the packages that we are going to load here. Okay. So, what we are going to do now is we are going to load the imputed data, okay, because we are going to use the GLMNet package, otherwise it might give us an error. Okay. GLMNet package when we use for lasso, we also had to use the imputed data. Okay. So, we have now loaded the imputed data here, and let us look at that. We have seen this data again. Imputed data means there would not be any NA values, right. So, those have been estimated correctly. Okay. So, in this data, what we are going to do is we are again doing some filtering. Okay. So, just look into the names that we have. What you notice is that this is a data that I have just created from the original imputed data by adding this DMYPD class at the end, right, because this is something that we want to predict, right. And so, we will do some filtering first, right. We will first, again we are familiar with this filtering, where if we have NA, then we are not going to take them, but of course, because this is an imputed data, it does not really matter. So, yes, we can start from this, right. We will select this from data box to DMYPD class. So, all these features are there plus the label, right, the class information that we need, and then we have a standard filtering, right, where we can simply filter the data, and we can take the full input data and we can run this, right, tab filter 2, and what we can do then is what we require, because these are specific requirements of the package, is we can define this input data DMYPD class as numeric, and simply saying these are numeric values 0, 1, 2, right. Otherwise, we might get an error in the GLMNet package. Okay. The next step is very familiar, right. We are again splitting the data into training and testing data. Okay. And this is how we are going to do this against GLMNet and do the regression. Okay. So, here it is, right. So, we have now training data and test data. So, first we will build this x and y. Okay. So, x and y is DMYPD class train, and only take these x values, right. So, from for the features and not the DMYPD class. So, that should not be an x value, right. So, this is how we are going to define x values, right. X values means these are independent variables, and the y value is simply the train DMYPD class. What you will also notice is we are defining for train, right. So, what is saying is model matrix, or if you are modeling this DMYPD class as a function of all the features in the training data of this model matrix, take only the feature names, not the actual label name or the y, right, and that is why y is train DMYPD class. Okay. So, we have defined x y. As we have seen before, in case of lasso regression, here we are also going to do this, right, and we need to define something called lambda mean, right. This is what we actually get from cross validation.glmnet, right. If you go back to the linear regression class, you will also see we did something very similar, right. We did something using cv.glmnet, right, and we got actually some coefficients, and as we apply lasso, some of the coefficients will be 0, right. This is something that we have seen in linear regression. Here the idea is very similar, right. cv.glmnet xy alpha equals to 1, family is multinomial. Okay. So, this multinomial means we are doing multinomial regression. Okay. And you might ask what is this set.seed means, right. Set.seed means if we run this multinomial regression multiple times on the same data, it will initialize with the same values, right. Okay. So, it is running this and it might take a bit of time, right, cv.glmnet, and we can actually plot this cv lasso and see how this looks like, and we have to choose the lambda minimum. Okay. So, once this run is complete, we need this lambda minimum. Like linear regression, when we did the lasso regression, we did the same thing, and then we will look into the coefficients of here. Once we have identified this, what we are going to do, then we will use this to run the final model on the training data, right, using this glmnet xy alpha equals to 1, family is multinomial, that is multinomial regression, lambda value that will come from this cross validation results, right, and this is what we are going to now look at, right. So, this run is complete, right, the cross validation, and as you can see, right, this is the multinomial deviance versus the log lambda. So, we need to choose this lambda minimum, okay, and we will ask this here, okay, and lambda minimum is in this region, right, where we have the minimum multinomial deviance, right. This is the where the lambda minimum is. So, this is actually log lambda. So, this is log lambda is around minus 4. So, the actual lambda minimum is around 0.016. Okay. All right. So, then we can look into the coefficients. We have identified the lambda minimum, we can look into the coefficients, right, and you can see, right. So, some of these coefficients are missing, right, these are not important features in this model, and those will be discarded. Okay. So, now once we have identified this lambda minimum, we can now run the final model using the same command, right, model glmnet xy alpha equals to 1, family multinomial, and lambda equals to lambda minimum, right, the lambda minimum that we have determined from the cross validation step before. If you go back to linear regression, you will see this is something that is very similar to what we did before. Okay. Okay. So, we have now run the model, we can look into the coefficients and we can now apply. So, again we have seen these coefficients, right, some of what it dot means, some of these coefficients are not there, which means they are not important predictors for this model. Okay. Now, predictions, what we have to do now is we have to take this data again and predict on the test data. Okay. All right. So, this is where again we have to define this x test, right. In similar way we define for training data, okay, and model matrix demorphic class on the test data now, and we will not be taking those taking that column where we actually have the y, right. So, this predict the response variable which should not be part of x, okay, and then the probabilities, right, is model predict nu x equals to x test, right. So, based on this the model, there will be prediction on the x test values, right, and these probabilities will be the predicted y values. So, we can look into these probability values actually, and okay, we can just apply the head, and this is like the predicted values for 1 to 3, right. So, this remember we have 3 classes here, class 1, class 2, class 3, and it is predicting, right, which sample belongs to which class here, right. So, as you can see for this sample 1, right, this is predicting to be 0.55 here, and this is the highest value. So, this means this will be predicted as this sample will be belonging to class 1, that will be the prediction. Now, what we will do next is we just want to simply summarize this, right. So, as we have summarized before, right, how well this model is predicting. If it is binomial model, right, or binary classification, this is actually very simple. You can say predicted classes, which of these probabilities. So, because there are two classes where the probability is greater than 0.5, then position you can say positive, negative, but this is a multinomial regression, right. The formula is slightly different, as you have seen. So, this is what we have to do, okay. And what we have is number of rows in this probabilities matrix and number of columns in this probability matrix, as you have seen, right. And we are simply running a very simple code, and we are kind of predicting this predicted class, right, based on the maximum value, okay. And this is what we are doing, right. We have seen very simple code, okay. So, maybe we have to first define these predicted classes, okay. Okay, so because we have not defined predicted classes, so that's why probably is giving me an error, okay. And then we run this, and okay. So, you see these predicted classes here, and again we can look into the observed classes, and we can see how well this model is performing, right. So, yes, observed classes are actually test GMIPD classes, and on the test data, right, predicted class is equal to observed classes. This is about 0.495. This is about 49.5% accuracy. It's still not that great, right. So, it's about 50% accuracy. We still can improve, right, this model. Now, of course, one of the things we might also need to keep in mind, maybe the feature set that we are working with is not the best feature set. We may have some missing features that are not here, right. So, what we can do next is we will apply stepwise regression and see if we can improve this, okay. And as I said, we will apply this library NNet, right, and let us okay. And we have already defined the data, we already have the training data defined, test data defined. So, we will simply run this, and by saying model equals to multinom DMYPD class, this is our response variable or y, right. This is where we have the actual class information. This is what we want to predict. Dot is use all the features, data is training, okay. It will take, it might take a bit of time, okay. So, it says stopped after 100 iterations, right, and this is kind of predicting the class here, and we can see this summary of this model, right. Okay, maybe it looks pretty complex, right. So, what you see is this, we have these coefficients, right, intercepts and the features coefficients, right, for each of these features that have been used, and then we can do coefficient model. Yeah, so we have seen the coefficients already, and what we can do is we can calculate the probabilities, and we can again look into the probabilities, right. And predicted classes will be simply as numerical probabilities, right. So, you can see this is something slightly different in structure. Here it's actually predicting the class itself, and then we can again look into the how many of these predicted classes is equal to test DMYPD class. So, it's again it's about 44%. So, it's actually not that great, right. So, we can still improve this model, right. So, just to again look into the summary, right. Okay. Just to remind you, right. So, we have seen the accuracy is 44% is still not great, which means perhaps there are some missing features, or maybe logistic regression or multinomial regression is not the best way to predict these classes. Here perhaps we need some other measures of classification, right, and this is where perhaps decision trees will be useful. Just to show you, right, this is the formula that we called, and these are the coefficients, etc. Looks like normal multinomial regression, but here finally we have something called these AIC values, right. and this is something that is we have used for stepwise regression before, right. So, stepwise linear regression, we have used these AIC values, and here also we are getting these AIC values. This is what this model also is using as a criteria. So, we have done the using the multinomial regression with this NNet package, but that is normal multinomial regression. So, what we want to run now is the stepwise regression as we have talked about, and for doing that we will use this library mass where we have the step AIC function, and we will now add this command, right. So, earlier what we ran is this model multinomial data train, and then on top of that we want to use this step AIC. So, this is something we will do the stepwise regression and trace equals to 1, and I will run this, but this will take a lot of time. So, I will just run this and leave it at that, and you can also run this and see what you get at the output. Okay. So, trace equals to 1 means it will show us like what is going on, right, what are the steps it is doing. Okay. So, we also have the library NNet, and then so this is where it will now running, and here you will see these variables that are being chosen, right, and then this will be finalized, right, after trying out a lot of these combinations. So, the first set, as you have seen here, is shown, right, what are these variables that you have, and then you have the AIC values, that is the start one, and this is actually will going to take a lot of time because there is a lot of variables in this data set. So, we will just leave it at that, but this is how you can run this step AIC. Okay. So, we have now covered, right, the how to run multinomial regression, penalized regression, as well as stepwise regression in R. Okay. So, with that we will move to the presentation. We have looked into the hands-on part, and we will simply summarize what we have seen in this class, right. So, what I mentioned, right, on this first hands-on we got very high accuracy, right, when we applied logistic regression on cancer data we got very high accuracy, but here when you are applying logistic regression on noise data our accuracy is not that great. Okay. And this is something that we have talked about in linear regression as well, that this is something that could be because of overfitting, right, and some of these features are probably not really required, and on test data the accuracy suffers because of that. Okay. And we have seen, right, we applied logistic regression for classification of biological data, and to avoid this overfitting we have tried out penalized regression and stepwise logistic regression, which provide solutions against overfitting. In the next class we will be now talking about decision trees, and we will see if decision trees can improve the prediction accuracy of this data set. Thank you.